lecture I am going to discuss the solution of the one-dimensional wave equation using the separation of variable method, and then we will try to solve one or two questions. So, solution of one-dimensional wave equation. The wave equation is del 2y upon del 2e2 equal to c square del 2y upon del x2. So here you can see that your y is depending on t and x. So let us assume, say this is equation 1, let solution of 1 is say y equal to some t of small t and into capital X, which is your function of small x, and we can simply write it as t into capital X. So del 2y upon del t2 will be your t double derivative into x, and del 2y upon del x2 will be t into x double dash. Hence by 1 we will have del, now by 1 this will be your, now del 2y upon del t2 will be your t double dash x equal to c square t x double dash. So from here we have t double dash upon c square t equal to x double dash upon x, and let us assume their common value as small k. So from here we will get t double dash minus c square into k t equal to 0 and x double dash minus k times x equal to 0. Now our solution depends on the nature of k, whether k is positive or k is negative. So let us assume case first. Let us assume that k is greater than 0. Now if k is greater than 0, then we can assume k as lambda square, where lambda is non-zero. So let us assume k as non-zero, then we can take k equal to lambda square, where we are assuming that lambda is not equal to 0. Then your t double dash minus c square lambda square t equal to 0 and x double dash minus lambda square x equal to 0. So from here you can write it as d square minus c square lambda square t of equal to 0, and here you can write d square minus lambda square of x equal to 0. You take it as some another d, say d square, where my rounded d is the partial differentiation with respect to x and d is partial differentiation with respect to t, that means the small t. So its auxiliary equation will be your m square minus c square lambda square equal to 0, and here we will get m square minus lambda square equal to 0. So from here we will get the roots as c lambda and minus c lambda. From here we will get the root as plus lambda or minus lambda. Now as the roots are distinct, so your CF means the final solution, as the right hand side is 0. So from here our T1 will be C1 e to power lambda Ct plus C2 e to power minus lambda Ct, because our roots are distinct and they are at, the roots are plus C lambda and minus C lambda. So this will be your C1 e to power plus lambda Ct plus C2 e to power minus lambda Ct. So this is your T, and from here our x will be, we have already assumed C1 and C2, so let us assume the constant as C3, which will be your, x will be your C3 into e to power lambda x plus C4 into e to power minus lambda x. So these are the solution of these partial differential equation. Therefore our final solution will be your y will be, your yx will be x into t. So we can write it as c3 or t into x. So this is equal to c1 e to power lambda ct plus c2 e to power minus lambda ct, then c3 e to power lambda x plus c4 e to power minus lambda x. So this is the solution when your c is when your k is greater than 0. So this is the first case when we are assuming that k is greater than 0, and we have assumed that k equal to plus lambda square. Now case 2, in case 2, let us assume that k is less than 0 and k equal to minus lambda square, and again lambda is not equal to 0. Now if k is minus lambda square, then this will become your plus, and here we will have plus sign, so this is your plus and this is your plus. Now your roots will be, m square plus c square plus lambda square will be 0. So m will be I times c lambda, and m equal to minus I times c lambda. From here we will have m equal to plus minus lambda I. So as the roots are complex conjugate, therefore your t will be c1 cos lambda c lambda t plus c2 sin c lambda t, and from here our x will be c1 and c2 are already used, so this x will be c3 cos lambda x plus c4 sin lambda x. Therefore solution is, so your yxt will be c1 cos lambda ct plus c2 sin lambda ct plus into c3 cos lambda x plus c4 sin lambda x. So this is your solution in this case, which is your c1 cos lambda ct plus c2 sin lambda ct plus c3 cos lambda x plus c4 sin lambda x. Now let us consider the case 3, when your k is equal to 0. Now if k equal to 0, case 3, let us assume k equal to 0. Now if k equal to 0, then from here we will get t double dash equal to 0, and from here we will get x double dash equal to 0. Now t double dash 0 means integrate this t 2 times, then from here we will get t equal to as c1 plus c2 small t, and from here we will get x as c3 plus c4x. So your solution is yxt equal to c1 plus c2t and then c3 plus c4x. So these three are the possible solution of the wave equation. So we have three possible solution for the one-dimensional wave equation. Now, as we are dealing with the transverse motion of the wave equation, that means as we are dealing with the transverse motion, so this means the solution must be periodic. So as the solution must be periodic, so we will only take this as a solution of the one-dimensional wave equation. So we will reject the remaining two solutions. So our solution will be this one. So as we are dealing with transverse motion of the string, so our solution must be periodic. So let yxt equal to, so yxt equal to c1 cos lambda ct plus c2 sin lambda ct, c3 cos lambda x plus c4 sin lambda x is the solution of one-dimensional wave equation. So this is the solution of one-dimensional wave equation. Okay. Now let us solve one question. So solve. Our question is, a tightly stressed string is fixed with fixed endpoints at x equal to 0 and x equal to L is initially in a position given by. Now I am solving two questions. In the first case, let us assume that initially it is in a position given by y of x0 equal to y naught sin cube pi x upon L, and for the second case, for the second question, let us assume yx0 is equal to kx L minus x. So a tightly stretched string with the fixed endpoints at x equal to 0 and x equal to L is initially in a position given by these two conditions. Now, if the string is released from its rest position, then find the deflection or displacement yxt at any time t greater than 0. So right now we have two questions, and the nature of the question depends upon the initial displacement. In the first part, our initial displacement is in trigonometric form, and in the second part, our initial displacement is in algebraic form. So this question is having two type of condition. In the first condition, we have the trigonometric form of the initial displacement, and in the second condition, we have the algebraic form of the displacement. And now the solution is common, but we have to evaluate the constant differently. So the solution of the problem, our initial conditions are, our boundary condition are initially when the length of the string is 0, when the length of the string is 0, then you consider your displacement will be 0, and when your length is L, that means at O and at point B, again your vertical displacement will be 0. So at the initial point, that means at origin, your y will be 0, and at the final point at B, where your length of the string is L, your displacement is 0. So these are your boundary conditions, as we have discussed the condition at the length x equal to 0 and x equal to L. Now here, say this is your condition number 1, this is your condition number 2. Initial conditions are, now your string is released from the rest position, so that means the string is released from the rest position, that means your velocity is 0. Your initial velocity is 0. And then the fourth condition, your initial displacement is given as y naught upon, say this is your fx, and which for the first part, say this is your fx, say, and for the first part your fx is y naught upon 4 y naught sin cube pi x upon L, and for the second part your yx is where your fx is kx into L minus x. So here I am assuming this initial displacement as yxt. Sorry, this will be your initial displacement. That means when this your time is 0, and again when your time is 0. So the initial velocity is given at 0, and initial displacement is your fx, and fx for the first part your fx is y naught sin q pi exponent, and for the second part your yx naught yx0 is kx into l minus x. So let us find out the general solution, and then we will change the values of fx for the both parts. Now solution of wave equation is yxt equal to, I think this was your c1 cos lambda ct plus c2 sin lambda ct, then c3 cos lambda x plus c4 sin lambda x. So this was the solution of the one-dimensional wave equation. Now let us use these conditions one by one. Using condition 1. Now if you use condition 1, that means when your x is 0, your displacement is 0. Now if x is 0, then your displacement is 0. So by this equation number say a or 1, using condition 1, we have, now using condition 1, your displacement will be 0 when your x is 0. Now if your x is 0, then sin 0 will be 0. So we have c3 cos lambda x, c1 cos lambda ct plus c2 sin lambda ct equal to 0. Now as you know that this cos lambda x cannot be 0, so from here our c3 will be 0. So c3 is 0. Now if c3 is 0, then this term will get vanished, and we have, therefore your solution will be yxt equal to c4 sin lambda x into c1 cos lambda ct plus c2 sin lambda ct. Now using the condition 2, we get, now if we use the condition number 2, then condition 2 was when your length is L, again your displacement will be 0. Now if your x is L, then we will have c4 sin lambda L, then c1 cos lambda ct plus c2 sin lambda ct. Now please note that this c4 cannot be 0, because if this c4 is 0, then your displacement will be 0 for any t or for any x. So this c4 cannot be 0. Now if this c4 cannot be 0, again this will be not 0, because if this is 0, then again your displacement will be 0. So from here our sin lambda L will be 0, and sin is 0 for n pi. So from here your L lambda will be n pi. So that means your lambda is n pi upon L. So we have the value of lambda. Now let us use the condition number 3. Now for the condition, now let us put this lambda here. Therefore your yxt will be, I think I am not using this condition. Now let us use the condition number 3. Now to use the condition number 3, let us differentiate this equation with respect to x. Now, so this is equation number 2. Now from here your del y upon del x will be, now differentiation with respect to x. So not with respect to x, because we have to find out the initial velocity. So let us differentiate this equation with respect to t. Now this will be your c4 sin lambda x. Now the differentiation with respect to t will be your minus lambda c. Differentiation of cos will be sin lambda into c4 sin lambda ct. This will be c2 into lambda c cos lambda ct. Now at using condition 4, using condition not 4, using condition 3. Now the third condition was your initial velocity is 0. That means when time is 0, your velocity was 0. Now if we put time t at 0, then this will be your 0, and we will get c4 sin lambda x into lambda c into c2 cos lambda ct equal to 0. Now again c4 cannot be 0, because otherwise your solution will be 0. So from here we will get our c2 equal to 0. So this C2 is 0. Now if this C2 is 0, then this term will get vanished. Thus by 2, our solution will be yxt equal to, now C2 is 0, then this will be C1 C4 sin lambda x into cos lambda ct. Thus our general solution will be, the general solution means we can have another constant. So in the most general solution will be the summation n equal to 1 to infinity sin lambda x into, say this C1 into C4, let us assume this as C1 Cn into sin lambda x. Lambda was your n pi x upon L, your lambda was n pi upon L into cos n pi upon L, that means n pi ct upon L. So this is the solution of your problem. So this is the general solution for the both part of the question. Now for the first part, our yx0, now let us solve the first part. For the first part, our yx0 was y0 into sine cube pi x upon L. This was your yx0, that means the initial displacement for the first part. So by this equation number 3, by 3 we get, now this yx0 is y0 sine cube pi x upon L, and in the right hand side if we put t equal to 0, then this will be a cos 0 and cos 0 is 1, so we will get n equal to 1 to infinity sin Cn sin n pi x upon L. So from here, now use the formula of sin 3 theta. Now sin 3 theta is 3 sin theta equal to 3 sin theta minus 4 sin cube theta. So from here, your sin cube theta will be 3 sin theta, so 3 sin pi x upon L minus 3 sin theta minus sin 3 theta sin 3 pi x upon L divided by 4. So let us take 4 here. Now again, in the right hand side, let us open the bracket. Let us open the summation. So this will be your C1 sin pi x upon L. Then we will have C2 sin 2 pi x upon L. Then we will have C3 sin 3 pi x upon L, and so on. So on comparing the coefficients on both sides, on comparing coefficients, we have, so your C1 will be 3y0 upon 4 and C2 will be 0, and then C3 will be minus y0 upon 4. So here we have the value of C1 and C3, and rest constants are 0, and Ci will be 0 for I not equal to 1 and 3. So rest constants are 0. So this will be your solution. Now just put the value of C1 and C3 here. So therefore solution is yxt equal to, this was your solution. Now put n equal to 1. So if n is 1, then this will be your C1. So C1 is 3y0 upon 4. Now if n will be 1, then this will be your sin pi x upon L into cos pi ct upon L. This is your C1. Now C2 is 0. So if n is 3, then your C3 will be minus y0 upon 4. Then this will be your sin 3 pi x upon L into cos 3 pi ct upon L. So this is your answer for the first part. Let us cross check it. So the solution for the first part is 3y0 upon 4 sin pi x upon L into cos pi ct upon L minus y0 upon 4 sin 3 pi x upon L into cos 3 pi ct upon L. So this is the solution of the first part. Now let us solve the second part. For the second part, our yx0 was, kx into L minus x. So from here, so by equation 3, now put t equal to 0, then in the left hand side we will have kx into L minus x. On the right hand side we will have, now this is your, if t equal to 0, then this will be your n equal to 1 to infinity Cn n pi x upon L, because our t is 0, so cos 0 will be 1. Now see the right hand side. In the right hand side, this is your half range sine series. As we have only one term of sine, so that means your right hand side is half range sine series. So if the right hand side is half range sine series, then the Fourier coefficient will be Cn equal to 2 upon L, then 0 to L, fx into sine n pi x upon L dx, where your fx is k. Let us take a common, that means your x into L minus x, so sine n pi x upon L dx. Now let us compute the Cn. Find out your coefficient Cn and then put it here, so that will be your solution. So let us find out this coefficient Cn. So Cn will be equal to 2k upon L. Let us find out it here. So Cn equal to 2k upon L. Then let us, this can be written as Lx minus x square. So Lx minus x square, use the Bernoulli rule of integration. Then integration of sine n pi x upon L will be minus cos n pi x upon L into L upon n pi. Then differentiation of this one will be your L minus 2x. Then integration of this bracket will be sine n pi x upon L. This is in the bracket. Sine n pi x upon L. Then we will have n square upon n square pi square. Then again we will have plus sign. Now the differentiation of this one will be minus 2, and the integration of this one will be cos n pi x upon L into L cube upon n cube pi cube, and the limits from 0 to L. Now here you can see that your upper limit will be 0, because at x equal to L, this will be your L square minus L square, so this is 0. Now this term will be 0 for the upper limit as well as for the lower limit, because if your x is L, then this will be your sin n pi, and sin n pi is 0. Now this term will exist for both the lower and upper limit, and this again the lower and upper limit of this term will be 0, because at x equal to L this is 0, and for x equal to 0 again this is 0. So now the last term will exist, so this will be your minus 4k upon L. Now for the, and again from here we will have L cube upon n cube pi cube. Now if your x is L, then this will be your cos n pi, which is your minus 1 power n, and if x is 0, then this is your minus 1. So this is equal to 4k L square upon n cube pi cube. Then in the bracket we will have 1 minus minus 1 power n. Now if n is odd, then this will be your 2 times. So this is equal to 8k L square upon n cube pi cube if n is odd, and this will be 0 if n is even. So our solution is yxt equal to n equal to 1 to infinity Cn. Our solution was Cn cos n pi x upon L. I think C1. What was our initial solution was Cn sin x pi upon L into cos n pi ct upon L. This was our solution. So put the value of Cn. Now Cn is equal to this term for n equal to odd. So let us take the summation as odd. That means let us take n equal to 1, 3, 5 and so on. And then we can take 8k upon common, so 8k L square upon pi cube will be common, then in the bracket we will have 1 upon n cube. So if n is odd, then this will be 1 upon n cube sin n pi x upon L into cos n pi c t upon L. So this is your answer of this problem. So this is your